Hi, so this is the fifth and final video of our AP Calc summer assignment. Today we're going to talk about the limits involving infinity. Before we do that, here is the answers to your assignment from the last video. If you had any trouble with this, go to Slader and ultimately circle anything that you need to go over the first day of class. So, like I said, we're going to do limits involving infinity. The key to this is knowing about asymptotes, so we're also going to review asymptotes in this video. The first thing we need to do, if we're looking at this example, is know how to graph it. So I'm going to use the calculator to graph it real quick. If we go to y equals, we type that in. You either need parentheses around the bottom of the fraction, or you need to use that alpha y equals button. So I got my lovely graph going here. And if I needed to graph this without my calculator, I know that 1 makes the bottom 0. So 1 is the location of my vertical asymptote. And then I pick a random value. So if I want something below 1, so maybe 0, I know 1 divided by negative 1 is negative 1. So I know that graph goes kind of like that. And if I pick something greater than 1, maybe 2, I have 1. 1 over 1, which is 1. So I know that's my graph right there. So then I can answer my questions. The limit as x approaches 1 from the negative direction. So if I'm coming at that from the negative direction, my graph is going down to negative infinity. If I'm doing x from the positive direction, my graph is going up to positive infinity. So I know that my left-hand side and my right-hand side are not equal. Therefore, if the question said, what's the limit as x approaches 1? I would say that does not exist because my left-hand side is going to negative infinity, my right-hand side is going to positive infinity. They're not equal, so it does not exist. Remember, the key to this is you're going to have to know how to graph this without a calculator. So let's look at another example. 1 over x minus 1 squared. So once again, let's show you graph this one without the calculator. We know x equals 1 makes the bottom 0. So I'm going to put my vertical asymptote at 1. If I plug something greater than 1 in, maybe 2, I have 1 over 1, which gives me positive 1. I know 3 would give me 1 over 1/4, so it's definitely getting closer to infinity. Likewise, if I do 0 again, this time 0 minus 1 squared is 1, so I have 1 over 1. If I put in like negative 2 or negative 1, so that's 1/4, so that side's still getting closer to 0. So there's my graph. Alright, so let's look at this one. If we come at x from 1 in the negative direction, we know our y is going up to positive infinity. If we go towards 1 in the positive direction, we know that our graph is still going up forever, so positive infinity. So therefore, the limit as x approaches 1, the left and right-hand side of this one is the same. So since the left side is infinity and the right side is infinity, we can say our limit is infinity. So this one is nice because our limit, well, it still does not exist because it's going to infinity or negative infinity, but they're both going to positive infinity. So we know more about our graph here. So let's refresh our memory about some different things. If the degree of the function is greater than 0, then the limit is positive infinity or negative infinity. If the degree of the function is less than 0, then the limit is 0. So let's look at what that means. So if we look at this exponent is 1, which is greater than 0. So since this number right here is greater than 0, we know it's going to be infinity or negative infinity. So let's figure out which one it's going to be. Well, we know this is a line, and we know more more about it than that, but we know it's a line. We know if we plug very big positive values in there, very big positive values is going to be in this direction, so we know our graph is going up forever, so we know it's going up to positive infinity. Now, if this equation had been negative 2x, well, now if I plug a really big positive number in there, a really big positive number times negative 2 would be negative infinity. So just watch that sign. That sign tells us whether it's positive infinity or negative infinity too. All right, so let's look at this one. This time, we know that there's a 1 on the bottom, and I can rewrite that as a negative exponent, so that's x to the negative 1. So since that is less than 0, we know our limit as x goes to infinity is 0. Which makes sense because as x gets bigger and bigger, so if we start with 1, we have 1. We go to 10, we have 1/10, 1/100th. As x gets bigger and bigger and bigger, this number is actually getting closer to 0. Okay, so in addition to the rules we just talked about, we're going to look at a couple of other rules. So that this is all of your rules for what we used to call the horizontal asymptotes. But if you imagine, a horizontal asymptote is showing what happens on the ends. So a horizontal asymptote is also what happens to the limit as x approaches infinity of the function. So if a function has a horizontal asymptote, that also tells us what happens as x approaches infinity. So these rules should look familiar to you, but we're going to look at them real quick. So if the degree of p, which is our top function, is less than the degree of q. So that means that the top exponent is less than the bottom exponent. So if we have fewer exponents on top than the bottom, then the limit is 0. If the degree of the top equals the degree of the bottom, so if the biggest exponent on top equals the biggest exponent on the bottom, then you're going to simplify the coefficients with the largest degree of the numerator and denominator, aka you're going to divide the leading coefficients. And the last rule is if the degree of the top is bigger than the degree of the bottom, then the limit will be positive infinity or negative infinity. So if the exponent on top is bigger than the exponent on the bottom, you're going to know it's going to be positive infinity or negative infinity. And you kind of have to analyze the problem to decide which it is. So let's look at a couple examples of these situations. So if we look at this first limit, so here, our top exponent, our biggest exponent on top is 3, and our biggest exponent on the bottom is 2. So our top is bigger than our bottom. And looking back at those rules we just went over, that means that it's going to be infinity or negative infinity. So I think about it. If I have a positive infinity, so this is really a really big positive number, and I'm cubing it. Now the rest of the things don't really matter, because the biggest exponent is going to control the sign when you get really, really big, when you get really close to infinity. So I have a really big positive number cubed, and then I have 6 times a positive number squared. Well, ultimately, I'll have a positive number on top and a positive number on the bottom, so I know that this limit will be positive infinity. You can always check this on your calculator. The graph should be going up as x goes to the right. All right, so let's look at the next one. We have x going to infinity, so we use our exponent rules. The biggest exponent on top is 2. The biggest exponent on the bottom is 1. So I know the top is bigger than the bottom. So I know it's going to be positive or negative infinity. Now it's just a matter of figuring out which one. So if I plug a really big positive number in for x, I have -2. I have a really, really big positive number squared. And on the bottom, I have 5 times a positive number to the first power. So a really big positive number squared is positive, but times -2 will make it negative. 5 times any positive number is a positive. So in this situation, I'll have a negative divided by a positive, so my limit will be negative infinity, because a negative divided by a positive is a negative. All right, so if we look at our next situation, in our next situation, the biggest exponent on top is 2, and the biggest exponent on the bottom is 2. And according to our rules, when the top equals the bottom, when the top exponent is the same as the bottom exponent, when their degrees are the same, we divide the leading coefficients. So what number is in front of x squared? 5. What number is in front of x squared? 3. So this limit will be 5 divided by 3. If we come over here, same thing. X is going to infinity. So we look at our exponents. Our biggest exponent here is 3. The biggest exponent here is 3. Or the bottom is 3. So we just divide our leading coefficients. In this case, the number in front is 4. In this case, the number in front is -2. 4 divided by -2 is -2. So that's how we do the limits of infinity. In these two situations, if it's negative infinity, the answer is still the same. Up here, if it's negative infinity, our answer would be slightly different. So let's look at one other quick example. So if in this problem, let me just drag it down. If in this problem it became negative infinity instead of positive infinity, so now we have to still, our top exponent is still bigger than our bottom exponent, but now we're plugging a negative number in, a negative cubed plus a bunch of stuff, and then we'll have 6 times a negative squared. So a negative squared is positive, so we're going to have a positive number in the bottom, but on top we have a negative cubed, and a negative cube's negative. So negative divided by a positive is a negative. So that sign in front of this infinity does matter. That controls whether it's a positive or a negative number getting plugged in for x. All right. So we also need to know how to evaluate the limit of an exponential function. So if you don't remember, e is approximately 2.72. So this is really just 2.72 to the x. So hopefully you remember that this is an exponential function. If you don't, you can plug in some numbers. E to the 0 is 1. E to the first power is e, so about 2.72. E squared is, well, 2 squared is 4. 3 squared is 9. So we know we're somewhere in the 4 to 9 range. Regardless, we know that this is going to be what our function looks like. So as x goes to positive infinity, our function is going up, so the limit is equal to positive infinity. As x goes to negative infinity, the function is getting closer to 0, so our limit is 0. You have to know how to graph these kind of in your head. Draw a sketch and then imagine where it's going to be. So likewise, if it's negative x, that's a reflection over the y-axis. So now my graph is going to look like this. If you didn't know that, you can plug in some values, like we know if x is -2, then it's really e to the -2, or e squared, which we said was 4 to 9 in that other problem. E to the -1 would be 2.72, e to the 0 would be 1. So that's how you can kind of do a quick sketch of that. As x goes to infinity, the y value is getting close to 0, and x goes to negative infinity, the y value is going up forever, so we say infinity. So in order to do these, we need to know asymptotes. We have already talked about horizontal asymptotes. Those are the exact same rules as our limits to infinity. So if the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. If they're the same degree, if they're equal, then we divide the leading coefficients. And if the top is bigger than the bottom, the top is bigger than the bottom, then there's no horizontal asymptote. That's the difference. If we're looking at horizontal asymptotes, there isn't one if the top is bigger than the bottom. Likewise, we need to make sure we write an equation when we're talking about asymptotes, because asymptotes are a line. So we need y equals. To find the vertical asymptote, we set the bottom equal to 0, and we have to check for removable discontinuities. All right, so let's look at an example. This one wants us to find the horizontal asymptotes of these functions. So the horizontal asymptotes are simply our exponent rules. So we look at our exponent. The top is 1, the bottom is 2. So the top is smaller than the bottom. So looking back at our rules, we know that the bottom will get big really quickly. So think about this for a second. As x gets greater and greater, the bottom's getting really, really large, while the top's not getting as large as quickly. So we know it's y equals 0. Look at the next one. So the exponents are the same. If the exponents are the same, we look at the numbers in front. So we have 2 in front here and 3 in front here. So our horizontal asymptote is 2 over 3. And that would be it for that slide. So I want you to try G and H. Pause me for a second, go ahead and try them, and then come back. All right. So this answer should be y equals 3 over negative 4 or negative 3 over 4. The negative can go in either position. Typically we put it on top. Just make sure you have y equals. Without the y equals, it's not correct because it's on a line. This one, you have the same exponent, so it should be y equals 3 over 1, which is 3. So make sure, once again, you have y equals 3 and not just 3. All right, so vertical asymptotes are the zeros of the denominator. And in pre-calculus and in Algebra 2, that's how we always define vertical asymptotes. But in this class, we also want to note that if f of x approaches infinity, as x approaches c from the left or right, then the line x equals c is a vertical asymptote. So when we have our graphs, we're adding to our definition of what we know, that when we go to the left, from the left, or to the right, or from the right, and it's going to negative infinity or positive infinity, then there's our vertical asymptote. So that's adding to our definition of vertical asymptotes. So if we look at this one, the vertical asymptotes are always where the bottom's undefined, but we have to be careful. So here, I can set that equal to 0. X squared equals 1, x equals plus or minus 1. So in this problem, I have 2 vertical asymptotes. I have 1 and negative 1. Well, in h of x, we get really tempted to just do the same thing. Set the bottom equal to 0 and solve. But I have to be careful, because my top actually factors. So let's check that one out. Top factors to x plus 4, x minus 2. The bottom would factor to x plus 2, x minus 2. Well, I know I typically set the bottom equal to 0. So typically, I would have said x equals negative 2 or x equals 2. But this is technically not a vertical asymptote because they cancel out. So we call this is not a vertical asymptote. This is a removable discontinuity. When I graph this piece on my calculator, it's going to look like the normal graph, but there's actually an open circle there. So then x equals negative 2 is my only vertical asymptote. So if we look at this in our calculator for just a second, if I go to y equals and I plug that in real quick, I have x squared plus 2x minus 8. And on the bottom, I have x squared minus 4. If I plug that in and look at it, see at negative 2, I can see that vertical asymptote. Right there at negative 2, I can see that spot where it's a vertical asymptote. At a positive 2, I don't have an asymptote. See, if I graph this by hand, at positive 2, I have an open circle. Because at positive 2, if I hit trace and hit 2, it tells me there's no y value. So there's actually an open circle there. Our calculator just has trouble graphing an open circle, so it has to connect the dots. So you have to be smart enough to know that there's an open circle there. All right, so we're almost done. Last thing we have to talk about is end behavior. So if we look at end behavior, hopefully remember that end behavior is really just a statement that you're going to fill in the blanks for. And it's always the same set of blanks. So what the first blank says is what's happening as x goes in the negative direction. And then the second statement says what's happening as x goes in the positive direction. So for every single one of these, when we have to do end behavior, we're going to just write this statement and fill in the blanks. So we're just going to continuously write this statement for end behavior and fill in the blanks. So give me a second. I'll get that done. Okay, so let's think about each of these separately. We know that even exponents, so if it's even, and if the number in front is positive, because this is really 1x squared, right? We know that they sort of have a smiley face. That's a smiley face parabola. So if I had x to the 4th plus x cubed, I'm just making this graph up, but it might be something like that, but it's still going to be pointing up on all the ends. So any even positive function, if it's even and positive, the ends go up on both sides. So as x goes to the left-hand side, the graph goes up, so it's positive infinity. As x goes to the right-hand side, the graph goes up and it's positive infinity. Well, that makes negative x squared obvious, hopefully, because this is still even, but now it's negative, and we know a negative is a reflection, so negative x squared is a sad face. Another negative, a negative even exponent might look something like that. So whenever it's negative and even, we know that as x goes in the negative direction, y goes down. And as x goes in the positive direction, y goes down. Both the left-hand side is down and the right-hand side is down, so we just use negative infinity for both of those blanks. So if we think x cubed, well, x cubed is odd, and this one's positive, and I don't know x cubed as well as I know x, y equals x, and x has an odd exponent and is positive, and I know that one looks like this. Well, hopefully we remember from our other classes that their end behavior will be the same because they're both positive and odd. So I know the end behavior of x cubed, which in reality looks something like that, will be the same as the line, y equals x. So think about it this way. As x goes in the negative direction, y is going down. As x goes in the positive direction, y is going up. So that would be the end behavior for that function. And when we do negative x cubed, remember that will be a reflection. It will be the opposite. So as x goes in the negative direction, the y value goes up. And as x goes in the positive direction, the y value goes down. If you had Mr. Rash, you remember his disco moves. This is where that comes from. So x squared, they're both up or both down. X cubed, they're in opposite directions. So you got to remember evens both up and both down, and odds opposite directions. So likewise, we're almost done. Likewise, if I have a crazy fraction, in reality, and I have to do the end behavior of that crazy fraction, in reality, it's not too bad because I think about fractions as division. So if this is a positive x cubed and I'm dividing by a positive x, I could do long division here, but I don't really need to do long division here. All I really need to know is what those two divided will give me. So 6 divided by 3 is a positive 2. x cubed divided by x is x squared. So if I look at my numbers, I know this is positive divided by a positive is positive. The exponents, if I remember, I subtract exponents and I divide, so that's x squared. So this is going to have the same in behavior as a positive even function. Now, this is not this function. You can look at this function in your calculator. This function will not look like a smiley face parabola. It will not look like 2x squared because it's much more complicated than that if we truly did the full long division. But I can just look at the biggest exponents and divide those, and that tells me my end behavior. So since this is even and positive, I know it's going to have ends like a parabola. I don't know what happens in the middle. That's a big question mark, but I know the ends will be like a parabola that's smiling. So I know the left-hand side will be positive and the right-hand side will be positive. So likewise on this problem, this is really a 1. So I divide the numbers. So it's -7. And we know that this one is actually -7x cubed because we subtract the exponents. This one we can easily simplify. So this is in fact equal, other than this one has a vertical asymptote of x equals. Now a removable asymptote of x equals 0, because I was able to remove it to rewrite that as y equals -7x cubed. So anyway, this is negative and it's odd, so we know it's going to look sort of like that. And so therefore, the left-hand side is going up and the right-hand side is going down. All right, so that's the end of this lesson on end behavior and asymptotes. There's your assignment. Go ahead, pause me, do the assignment, come back later, check the answers. But here are the answers to that assignment. And if you need help with this assignment, you need to go to Slader, that website I gave you in your summer assignment. Go there, get some help. And if you still need help, circle them at the first day when we come back to class. We will go through them. So hope you have a lovely rest of your summer. Hopefully this is not the day before the first day of school and you're up really late doing this. I look forward to meeting you. For those of you I haven't met and for those of you I had before, I look forward to seeing you again. Have a great day.